Without further ado, I'd like to introduce Shuran. Please take it away.
Thank you. Thank you for the introduction and also the invitation. It's very nice to be here today. So before I start, I want to point out that there are 3 links on the first slides of my talk. So basically, that includes most of the robot videos that I'm going to use in today's talk. So just in case there are any issues with either Zoom or the internet, you can still check out the robot videos in full resolution, full frame rates from those webpage. Okay, so let's get started. So today I'm going to talk about dynamic manipulation for deformable objects. And so I think recently we have seen a lot of amazing progresses being made in AI and robotics. And I think for today's audience, I really don't need to go over all the list of all the progresses, especially in the field of robot manipulation. But I do want to bring up that if we take a closer look on most of the robots or the robot systems that we designed today, we can see that many of them are still quite rigid, and many of them actually still requires pretty careful design for a lot of seemingly simple tasks, right? So for example, in this video, the robot is actually designed to use very slow and careful movement in order to pick and place different objects. So this kind of slow action is actually on purposely designed to avoid any object dynamics, such as accidental movements between the objects and the gripper. So this is just an example of many kind of useful robotic systems today that are categorized by their very rigid movements and which are exclusively designed to handle rigid objects. So the goal of today's talk is trying to relax this kind of rigid assumption just a little bit for robot manipulation. So which come with 2 key aspects. I think one of them is the type of objects a robot can manipulate. And the other aspect is the type of action or movement a robot can take. So first, for the objects, although rigid body is probably one of the most common assumptions that people use in robot manipulation. However, in reality, there in our day-to-day life or in our environment, there are actually very few objects that can actually strictly categorize or following that rigid body assumption. Right? So for example, for objects like blankets or garments, they're actually very common in our life, but they are possess a set of very unique properties, making them hard to perceive and manipulate. So for example, they often have much higher degree of freedom and complex dynamics. And more importantly, they are also highly under-actuated. So what that means is that when a robot is kind of manipulating or holding a piece of cloth, for example, what it can control is only a small region of the cloth around its gripper, right? So the rest of the cloth, it kind of just hang there, and the robot actually do not have any direct control for those out of contact positions on those objects. So that actually is one of the properties that make deformable objects hard to manipulate. So as a result, many of those typical actions that we designed to handle rigid objects, such as pick and place actions, are actually often highly inefficient for deformable objects, because each time each of the action can only affect a small region surface on the object. However, on the other hand, we manipulate deformable objects in a very different manner, right? So if you look at the videos here, we often use very fast and fluid motions that fully leverage the dynamics of the deformable objects in order to quickly achieve our goal. So formally, we can kind of categorize these 2 types of manipulation strategies as dynamic manipulation and quasi-static manipulation. So basically, the difference is that in quasi-static manipulation, the system will always try its best to avoid the task dynamics by using slow movement, right? Basically, that assumes that if the whole system is static as soon as the robot stops moving. However, on the other hand, dynamic manipulation will try to embrace and leverage those kind of dynamics in order to manipulate the object efficiently. And when used properly, it can significantly improve the system's efficiency and expand its reach range. And a simple example of dynamic manipulation you can think about is tossing, right? So where the system kind of use the velocities in the end effector or the gripper in order to place an object in a faraway locations that's beyond its reach range, which is much more efficient if you think about it compared to those kind of rigid quasi-static pick and place. And this kind of advantage is actually even more salient if we start to consider deformable objects, or in general under-actuated objects or systems. So fundamentally, what it allows the system to do is to make use of the accelerations in action in order to control those out of contact positions on those deformable objects. Right. So here are just a few examples of those actions, such as fling a cloth, swing a rope, or kind of opening a deformable bag with active airflows. Right. So here we also kind of highlight the locations on the objects that is being manipulated by the system, however, are not directly in contact with the robot throughout the process. So in today's talk, I will kind of get into details for those examples and then show how we can allow the robot to learn those kind of dynamic manipulation strategies through self-supervised learning. And we will start with some relatively simple tasks like cloth unfolding, and then move towards a more challenging tasks that are like goal conditions and requires more precise control on the robot side. Okay, so let's start by talking about Flingbots, which is actually our first attempt of using dynamic manipulation for the task of cloth unfolding. So the task of cloth unfolding actually has a very simple objective, which is just to try to increase the visible surface area of a cloth. Right, so this task is actually a common first step for almost any cloth manipulation pipelines, because, like, for example, if you just want to identify or know the categories of this garment, for example, whether it is a t-shirt or a dress, the first thing that you'll need to do is unfold it, right? And if you want to fold the cloth, also you kind of need to unfold it first. However, just like many tasks in robotics, where the objective is simple, doing the task robustly and quickly or efficiently is still pretty hard for a robot. Right, so here is just a video of a two robot arm that is trained to do this t-shirt unfolding task with quasi-static pick and place actions. So you can see that the system is making some progress on increasing the surface area of the cloth, but they are taking a very long time to making very small progress. And in fact, if this cloth or this garment is larger than the robot's reach range or the maximum reach range, the cloth will actually never be fully unfolded, no matter how long the robot takes. So what that means is that in reality, if your blanket is larger than your arm length, then you will never be able to fully unfold it, which is not very ideal. So this system actually, the pick and place system that I just showed, it's actually reflects a common limitation for many prior works in cloth unfolding tasks. Right, where the robot uses only quasi-static actions like pick and place in order to kind of unfold a cloth or a t-shirt. So although there has been so many like sophisticated algorithms has been developed to model deformable objects or doing deformable object perception, the resulting system is often still highly inefficient, where they can easily take hundreds or thousands of steps just to unfold a very small piece of cloth. But obviously, that's not how we would unfold a big blanket or big shirt, right? So what instead, what we are most likely to do is something similar to this, right? So we will very likely to grasp the cloth or the garment with two hands and then try to fling it with high velocity in order to fully unfold it. So this example kind of just shows that what's really missing in our today's robot system is the capability of using high velocity dynamic manipulation strategies, right? Which is also the key idea that we build on for Flingbot. So using this idea of like introducing high velocity actions, Flingbot is able to kind of achieve over 80% of coverage for most of the garments or cloths that we test on with 3 interaction steps. So this system also works on cloths that is larger than its physical reach range, like the robot's physical reach range, and able to generalize to different shape of garments that is not trained on. So actually the system only trained on rectangular cloths, but later we tested with different shape of cloths. So here is our physical setup or the system setup in real world. So in our experiment, we use the 2 UR5 arms and also 2 RGB cameras. So the first camera actually take a front view of the workspace after the class being picked up. And the second camera is actually taking a top-down image. And the second camera is actually the main camera for the system that is used to predicting the grass positions and also used to compute the reward. So what the system, what the algorithm actually need to do is to take those images as input and output the parameters for those Fling primitives or the Fling action, which we'll talk about in a bit. And then after each of the action get executed, the top-down camera will capture an image before and after the action get executed, and then compute the delta coverage of the cloud before and after the interaction, and then use that as a supervision signal to supervise or train the network. So basically, the network will try to encourage the actions that are able to introduce larger or bigger delta coverage. And then in the end of like kind of each episode, the system also automatically resets its state or the class initial state by randomly pick up and drop the class back to the workspace. So the system is able to kind of learn by itself with only self-supervised learning, self-supervised signals from the top-down camera with very minimal human intervention. Just from time to time, we need to switch out the cloud, but we don't need to actually label any of the training data for them. So in order to perform a Fling action, we actually designed like multi-stage Fling primitives that the robot needs to execute. So basically, the robot needs to first find 2 grass positions on the class in order to pick them up, and then stretch the class, swing the class forward, and then before placing it back to the workspace. So in the end, what the system needs to learn is the parameters to control those steps, such as where to pick up the class, how far to stretch, how fast to fling, and where to place. So actually today, I will not bother you with the details of the methods, how we exactly learn all these parameters, but instead I will directly jump into the results or the system in action to show you the comparisons. And if you're interested in how we actually learn those parameters, you can check out our paper.
Wait, actually, just a real quick question. So with the 2-arm system, it's more like a multi-agent system. Mm-hmm. Do you try to mirror like the other arm, or is it like each arm is kind of working independently and they?
Yeah. So yes, the system has 2 arms, but the controller is actually centralized. So basically means that we are predicting the action parameters for both arms together. So the Fling primitive, the primitive itself is actually kind of fixed primitive that the 2 arm will execute a similar trajectory. But the grasping location is actually a prediction that is actually not mirrored. Like it's a prediction that we predict the parameters for both of the arms together. Because it's a centralized controller, they actually don't need to worry about each other. The controller predict parameters for both.
Cool. Thank you.
Yeah, there are some like careful designs of how to design the action primitives so that they don't collide with each other. I think that's very interesting, but today I'm gonna skip that part. Okay, so here is actually the Flingbot system in action, and we also compare it with systems that's using pick and place as we showed earlier. So as you can see that with kind of 2 interaction steps, well, actually, in this case, I think 4 interaction steps, Flingbot is able to achieve more than 90% of coverage. And while the pick and place system cannot really achieve a good coverage, even with significant more interactions. So here is a result on the t-shirt. So as I mentioned, the algorithm actually only trained on rectangular cloth, but it seems that it can generalize reasonably well to cloth that has a different shape. And here are more results. Again, on our project webpage, there are a lot more videos that you can see, like how Flingbot works in action and also how it compares with pick and place baselines. So through this very simple exercise of developing Flingbot, I think the most surprising thing to us, or what we learned, is that with a very simple algorithm of learning where to pick up the class and using a like kind of fixed Fling primitive, the system is able to work really well for this very challenging task of class unfolding. And I think this kind of the simplicity of this approach really highlights the effectiveness of dynamic manipulation. So at least for this very specific task or application of class unfolding. And I think taking inspirations from this project, it is quite natural for us to think about how we can take this idea one step further. Right? So in particular, how we can introduce other form of dynamic manipulation primitives in addition to Fling, and also how to enable other type of tasks beyond just class unfolding. Right, so which will directly lead to the next two projects as that I'm going to talk about today.
Sorry to interrupt, I have a question. Do you have any intermediate supervision in between all these steps? Because I think it would be hard to learn, all these individual parts of the algorithm, for example, choosing the right spot and then choosing how much you want to stretch it, just by having the reward of, the coverage area, right? So do you have any intermediate supervision there?
Yeah, so actually that's a good question. That's also the part I skipped. So actually we divide the primitive into several stages, but actually for some of those actions, there is actually very natural solutions. For example, for the stretching, for class unfolding, you probably just want to stretch it as far as possible, right? So we actually use the camera in the front and then just ask them to stretch as far as possible, and that part is not learned. And similarly for the Fling primitive, actually it's also not learned. It's actually a fixed primitive. And in the end, if you read the paper, the only thing that the system needs to learn is where to grasp it. And the grasping point basically determine how well it will unfold the class. Right. Yeah, and we definitely take simplify the problem, and that's what we learn. And it works reasonably well.
Nice, thank you.
How long did it take to train the grasping points on the clock?
Yeah, so actually, I think for this project in particular, we trained the initial policy in simulation, and then we fine-tune it in real world. I think in the paper we mentioned there are how many hours of real world data that we collected, but it's I think within a day of data collection on the real world robot. Any other questions? Cool. Thank you. Okay, so maybe we can move on and talk about the other two projects. So how we can introduce other form of manipulation and also doing tasks beyond unfolding. Okay, so in the next project, we're actually gonna explore another type of dynamic manipulation, which is kind of quite different from Fling. So actually, in particular, how to leverage aerodynamics to manipulate deformable objects. So why air, right? Why aerodynamics? So when we talk about manipulation, I think the first thing coming into our mind is, I think most of the time, contact-based manipulation, which means that the robot needs to actually physically touch the objects in order to manipulate them. However, I think air-based manipulation is also a common strategy that we use on a day-to-day basis in our life. Right? So for example, blowing leaves on your backyard, or deform a heated glass to a certain shape, or there are a lot of blowing a hairs. There are a lot of examples of how we use airflows or directed airflows in order to manipulate some hard to manipulate objects. And compared to this kind of traditional contact-based manipulation, I think air-based manipulation also has quite a few unique advantages, and especially for deformable objects, which I will gonna highlight here. So I think first is about efficiency and the safety, right? So as we see in Flingbots, one of the advantage of that system is that it can expand the system's reach range by using high-speed fling action. However, when the class getting larger and heavier, it will become harder and harder for the system to fully unfold the class with just one fling. Since it actually requires the robot to execute action with much higher velocity, and which may not always be possible due to certain hardware constraints, like the robot's maximum acceleration speed, or some safety concerns, like what if you're executing those high velocity actions next to human, right? However, by using an active airflow created by a typical blower, the system actually can create high-speed interactions on the class without executing any high-speed movement, which is much easier to achieve and also much safer next to human. So another advantage for using air for manipulation is the ability to simultaneously apply many force on a large surface area without direct contact, right? So here is an example that if you, in order to open a bag and also keep the bag in its open state, we can simply blow air into it. However, without using error, you can imagine that a robot will need to kind of simultaneously grasp many positions on this bag in order to keep it at its open state, which is a lot harder and expensive to achieve. So we call this capability of using error to manipulate objects as dexterity with the error in it. And in this work, we will study how to use it for deformable object manipulation. So on a high level, our method is built on two key ideas. So first is what we already talked about, which is by leveraging this kind of active airflow, the system can apply forces on those out of contact surfaces, making the manipulation task easier, especially for under-actuated objects. This is one direction. And the second idea is that by leveraging the deformations on those objects that can be observed by a camera, for example, the system will be able to kind of decode the information about those airflows, which is otherwise unobservable. So, and then using those kind of information, the system could continuously adjust its action in a closed loop manner in order to achieve a certain goal, certain task goal. So in this project, we actually try to validate or test the effectiveness of a dexterity using two tasks. One is the one that we're familiar with, which is cross unfolding, and the other task is bag opening. So for the cross unfolding task, we are actually particularly interested in those failure cases that we encountered in Flingbots, where especially when the class getting longer and bigger, the robot cannot really produce sufficient speed to fully unfold the class. So in this example, it's actually a long dress that the robot cannot really fully unfold, no matter how many times it tries with fling action. And however, if we let the robot to control an additional air blower and learn a closed loop policy to kind of learn how to control the directions of the blower, then the system can easily unfold a diverse set of class, including this large dress. And also note that in this new framework, we could easily replace all these three robots with some cheap hardware or like slow robots, since we no longer require them to execute any fast movement. And the air pump that we got is like only $20 that you can get from Amazon. So the whole system, if we want, we can make it cheaper. So here is the system setup. It's very similar to Flingbot. And again, the main camera that we use for inferring the policy is the top-down camera that's used to capture the top-down image of the class in the workspace. So similar to Flingbot, the system also needs to predict where to pick or grasp the class. But additionally, it also needs to predict the blowing actions from the top-down image. So here, and actually, you need to predict the blowing action in a closed loop manner, basically continuously observe the reactions on the class and then adjust these blowing actions in order to fully unfold the class. So here is actually an example of inferred blowing scores for different actions. Each line is one blowing directions. And you can see that the higher score, which is indicated with those red lines, is oftentimes pointing towards those unfolded areas on the cloud. Okay, in order to train this system, we actually use the simulated environment where the blowing effect is simulated as a stream of invisible particles. But clearly, you're probably already thinking that this kind of physical model is highly simplified. That does not at all reflect the accurate aerodynamics in the real world, right? So for example, it cannot simulate the Bernoulli effect, which is quite critical for the bag opening task, for example. So as a result, although this simulation environment is okay for training cross unfolding tasks, it is actually not sufficient for training the bag opening task, as we will see later. And in those cases, we actually need to directly train the policy with real world data. Okay, so here is another example of cross unfolding task and the comparisons with other systems that use a quasi-static pick and place and also the Flingbots. So in this case, we can see that Flingbot is only able to unfold this large class at most in half, where our approach is like the dexterity approach is able to fully unfold this large class within 3 steps. Okay, it's fully unfolded. Beautiful. Okay, so So here are more results of the system in action. Again, you can check out the project webpage for all the results and comparisons and all the videos. So similar to Flingbot, the system is able to generalize to different garments and cloths with different shapes or geometries, and we're only trained on rectangular cloth. And apart from unfolding cloths, I think this system also works for another pretty challenging task, which is bag opening, where the robots, the goal of the robots is trying to open a closed bag and then also try to maintain its open state, right? So this task, again, is a very important first step for many downstream applications. For example, if we want to put objects into this bag, the first step is to open it and also maintain its open state. And similarly, the algorithm need to learn a closed loop blowing policy from the top-down image that's captured from the top-down camera. However, unlike in the unfolding task, this time we'll need to train the policy directly with real-world data, since the simulated aerodynamics is way too off for this task. So we actually collect 4,000 real-world blowing sequences on one bag, and it takes us 10 hours to collect those training data. And the reward is actually automatically labeled through the side view image, and we don't need to manually annotate any of the images. So it's kind of still in a self-supervised manner that's able to train the system. Okay, so here are just some quick results and comparisons. So actually, surprisingly, we found that this task is really difficult for contact-based manipulation systems. Even if we use dynamic actions like shaking the bag back and forth, it's not doing much to open the bag. Right? So we also implement a heuristic-based blowing policy that's kind of just always blowing into the center of the workspace, which works slightly better, but still cannot reliably open like any type of bags as we give them with different sizes of materials. And in comparison, the learning-based closed-loop approach that we trained can kind of much more reliably open the majority of the bags that we test down. So here are just more results for this particular bag opening task. If I can play the video. Yeah, interestingly, we actually found that we didn't collect a lot of data for this task. We only collected data for one bag, but we found that the policy learned actually can generalize pretty well to different type of bags with different sizes, even materials. And also it can generalize across a variety of different grasping locations. Any questions so far for this project? So of course, error-based manipulation can be applied for objects that's not deformable as well, right? So here is another interesting example of manipulating granular media with airflow. So here you actually see a little Anki robots actually equipped with a little air blowers, and they're able to kind of blow all the small particles into one target zone that we ask them to kind of collect all the trash into one location. So the algorithm is able to use air pretty effectively, also in a closed loop manner. And imagine if you can scale up the system with bigger robots, stronger blowers. It's possible to kind of design a robot and kind of clean up your backyard or blowing your leaves for you. Cool. So yeah, that is about dexterity, where we kind of use the aerodynamics to kind of leverage the aerodynamics in order to efficiently manipulate different type of deformable objects for different tasks, and address some of those big challenges for traditional contact-based manipulation method. Any questions related to the second project before we move on?
Shuran, can I ask a question?
Mm-hmm.
How are you, maybe I missed this, but how do you measure the state of like how open the bag is again?
Your question is how we get the state representation, or how we measure how the bag is opened?
Yeah, like that number, the second part, like when you have like the scalar that of like 0.6 or 0.7, like how is that measured, I guess?
Yeah, so whether the how much the bag opened, we kind of measure it from the side view camera. So that is also how we get the reward values for training the policy. So we have a side view camera basically looking at how big what's the volume of this bag. And then we kind of, so the floating value that you'll see is basically dividing the current size of the bag with the maximum size. that it can achieve when it's fully opened. And then when it's fully opened, it's just in open state. And
I see. So it's not actually the opening, but just like sort of the side view area.
Yeah, so it's actually not the opening of the I guess the circle, but it's kind of measuring the volume from the side view.
Okay, thank you.
Any
Sorry,
other questions?
yeah, sorry if I missed this, but so you trained on this real world data of the bag, and then I think you're presenting the performance on that scenario, right? Did you try to generalize to any other kinds of bags or something?
Yeah, we only trained on one bag that I didn't show you, and all the bags that you see is actually new bags that is not trained on.
Okay.
Yeah, so we train on a cloth bag that is smaller actually than any of the bags that we test on, and then and we also test on plastic bags that has relatively different physical properties.
I have a more professorial question. What are the principles you have learned from all of this presentation? How can you encapsulate what are the necessary components of your system that anybody else can repeat your experiments?
Yeah, so I think one thing that I learned is that actually incorporating dynamic actions is first very useful, and also it's not that hard, right? So I think the way that we are taking our approach has been using is kind of designing some kind of dynamic action primitives. And then we kind of try to reduce the dimensionalities of those dynamic actions into some very few parameters, right? So in the first example, it's only the grasping positions. And in the second one is the blowing directions. So with those kind of primitive and with those kind of low dimension representation, it's actually not that hard to use and leverage dynamic action.
So for example, can you give us specification list for your force sensors? And in return, what kind of materials can you deal with? Can you specify the limits where it will work or it will not work?
So I don't think I fully understand the question. Do you mean that if whether the system can by itself tell whether it can achieve certain tasks or not?
Well, let's suppose I am an industrialist and I watch your video and I say, well, you know, I have a company where I have to deal with certain materials. I have to fold them. I have to pack them fast. What do I need to know in order to, and what are the limits I need to know that I can do that?
I think depends on the task. Actually, a lot of times.
Otherwise, it looks like a magic.
Yeah. So I guess
we are scientists.
Yeah. So I guess one way to think about it is whether your system can do this task once. I think for robots, if you are able to kind of, for example, design like using a lot of heuristic or kind of human understanding or knowledge, they're able to do this task once. You're able to design this primitive to accomplish this task once. Then the robot actually will be repeatable, and they will be able to do this task pretty well in the future as well. But I think just automatically, I think whether a task is doable or not, it still kind of rely a lot on our human intuition. I don't think the system itself can actually tell.
Okay, I will not push it further.
Any other questions?
So going back to Flingbot, it seems like you had some effort put into designing the motion primitive used for that task. can you speak at all to like how that choice of motion primitives, I guess, made training easier versus, say, like learning torques? And I guess what's your argument for why motion primitives versus learning to a more low level representation is the correct path?
Yeah, I think that's a design choice that we made. Whether we use a very low level control signals, or we kind of designed motion primitives and learn those few high level parameters. I think in our case, we make that decision so that it's easier for learning, so that the system don't need to learn everything from scratch, from bottom up. Indeed, the designing of the primitives come in with a lot of prior knowledge that we know what kind of actions we use, and oftentimes is inspired by how we handle in different objects or what kind of primitives that we use, and we found is useful.
Okay, that makes a lot of sense. Also, it looks like by making it so you just have like a single action, you don't really have to worry about like the credit assignment problem as much in RL. Did you notice like large gains in efficiency from that? Yeah, so indeed, because we train with dense reward for every single step, and also I think it's related to the task. The task that we're dealing with, at least so far we are looking at, is rather simple. It's actually, I think, one step reward already able to get the policy towards like a good performance. So we actually do not need to consider like long-term reward or long-term planning, and therefore we don't really need to use reinforcement learning, for example. Okay, thank you.
Yeah. So it's kind of like a greedy policy that always choose the best action to execute. Okay, all those are good questions. Yeah, and I think it's a good time to actually take a step back and actually look at both systems, right? So like what they have in common is that they all use dynamic action primitives or like manipulation primitives, and one use Fling, the other use error. And apart from that, I think they also share some common limitations or issues, which is that they cannot really handle like very precise goal condition tasks with some high precision requirements, right? So for example, in the class unfolding task, the algorithm only need to care about the total coverage without worrying about the configurations of the garment, right? Therefore, all these configurations that showed here in this example would be considered as equally good for this task, which is obviously not sufficient for many real-world applications that requires high precisions. So in the next project, we try to focus on another categories of much harder tasks, that is goal conditions. So in particularly, like what is a goal condition task in the context of dynamic deformable object manipulation, right? So here are two examples. One is trying to swing a rope to a target location, and the other is trying to swing a table class into a target configuration. So in both tasks, the goal configuration is defined by the target key point positions on the class or on the rope. And the key point is either the tip of the rope or the key points on the class. And since the target is still outside the system's reach range, it still requires the system to use dynamic actions. And in fact, there is a good reason why we try to avoid this kind of goal condition task in the first two projects, because it is just simply too hard, right? So, and we kind of try to look away from it. So specifically why it is hard. So first, unlike the quasi-static manipulation, object's motion under dynamic action is actually highly influenced by its physical properties. And also at the same time, for deformable objects, their physical properties are actually oftentimes defined by many hard to measure parameters, such as nonlinear stiffness or nonlinear density distributions, right? So as a result, this combo of dynamic and deformable objects, it makes it extremely difficult for robots to accurately plan its action in order to achieve a precise goal. And although, again, we're trying to look at how humans do this task, but actually this task is even hard for humans, right? So given a new rope, we are very unlikely to gonna hit the goal in the first try, right? And after a few attempts, will be able to get closer and closer to the goal and eventually reach the goal. So let's think about what we have learned, or like what we are learning throughout this process, or this kind of trial and error process, right? So are we learning the mapping from the action to the full trajectory? Probably not, right? Even I can hit the object, I probably still cannot predict the full trajectory. And also at the same time, are we explicitly decoding any of the physical parameters of this rope? I don't think so, right? Probably not either. I don't think I can predict like what's the stiffness, what's the density of this rope. I can probably not even like tell you how long, like precisely how long this rope is, but I can do this task after a few tries. So instead, what we are actually relying on, I think, is a good intuition or prior knowledge about how to adjust the action in order to affect the trajectory, right? So for example, swing harder will make the rope go higher, and extend our arm more will let the rope reach further. And we kind of rely on this intuition in order to adjust our action in order to get closer and closer to the goal. So in this project, we call this intuition, or this kind of good prior, as residual dynamics, which basically means that predicting how our change in our action will change the resulting trajectories, or if affect the result. And we're only learning this kind of delta action and also the delta trajectory mapping. So our hypothesis is that this kind of knowledge about the change is much easier to learn and also transferable to other ropes or other objects or other systems, especially if we compare to like learning the full trajectories. Okay, so based on this intuition, we propose an algorithm that called iterative residual policy, where the algorithm will learn a residual dynamics model that takes in observed trajectory of resulting from an action, and learns to predict an updated trajectory after applying a delta action. Right, the delta action is actually additional input to this residual dynamics model. And then using this prediction, the algorithm could iteratively refine and adjust this action using the visual feedback. So what we hope is that this kind of like residual dynamics, especially its general direction, could be much easier to learn and also able to generalize to new objects. And here the action for the robots is actually on a lower level compared to the primitives that we described earlier. So here the action is represented with the target joint angle and the maximum joint speed. So with this idea, we trained our algorithm in simulation and tested directly with real-world robot platforms. So here is the simulation data. So basically, you can see that here is a huge sim-to-real gap. However, with ability to adapt the system, it is able to kind of adapt the system online with visual feedback. It is able to adjust its action based on visual observations. So here is a system in action. So at each iteration, the rope trajectory is tracked by a calibrated camera. And the distance to go is measured by the shortest distance along the trajectory. And then the algorithm will sample a set of delta actions and then predict their trajectory using the learned residual dynamics model. And then the action associated with the smallest distance will be selected and executed for the next iteration. So in this visualization, we always show the best trajectory that gets selected on the top. Yeah, so finally, after a few steps, typically I think the system converges around 8 to 9 steps. So next, I'm going to show you some of the real-world robots results, and then on a variety of different testing ropes. And many of them is actually significant auto distribution compared to the training ropes that we use in the simulation. Actually, the ropes that we use in the simulation is modeled based on one of the ropes that we tested on, but many of them actually has very different density distribution, physical properties, and also aerodynamics. Like for example, the long thin cloth has a much higher air resistance compared to all the other ropes. And there's also a rope that's actually is a rope that with several knots. So the distribution is nonlinear. And here is the, if we let the system converge, and then here is the resulting trajectories that after the policy converges for different rows with the same target location or the goal, right? So all the policies that you are seeing is actually the same policy that's trained with simulated data only. So you can see that with different row, the algorithm actually choose to use different policy or action in order to achieve the goal. And then we also further try to further validate the system's generalization capability with respect to different robot hardware embodiments. So this is actually a really hard task because when we train the robots, we use one kind of embodiment, like with one the stick length. And when we change the length of the stick of the last link, basically, it's actually just drastically change the mapping between the initial action and the resulting trajectories, which means that in this case, the system is kind of forced to adapt to new robot embodiments in order to adapt to the new setup or system. So the only thing that they can rely on is the delta, the residual dynamics, and in terms of their general direction, right? So here is the result. So as expected, so actually for the rows that for the embodiment that has similar length compared to the training setup, it converges much faster. However, for all the different setups, the system is able to kind of adjust its action in order to get to a state that has a small error. And in the next experiment, we're trying to even further stress test the system about its robustness. So what we do is that we first let the system converge on a given row and a given goal condition. So now the system kind of converges. And then what we do is that we actually change the rope dynamics by manually tied a few random knots on the rope. So basically what that means is that this kind of change or interruption changes the physical properties of the rope, both in terms of their linear density and also length, right? So after that, immediately we can see that the system actually results in a pretty high error right after we make this interruption. However, after a few iterations, by observing the trajectory, the system is able to quickly adapt its action to accommodate this change. So here is some quantitative comparisons that we compare with other base test or alternative methods. So the method on the left uses optimal action in simulation that's optimized for each individual row parameters. However, it's still resulting around 20 centimeter error, which basically highlights the big sim to real gap for this task. And on the other hand, our method is able to consistently achieve a much lower error for all different ropes and embodiments. And finally, in order to kind of demonstrate the generality of the method, we're trying to apply the same method for a class placement task with minimal modifications. So the goal of the task is to place a class on a table given a target pose, right? So the pose here is defined by 9 different key point locations on the class. And again, the algorithm does not know the physical parameters of the class. So here are 2 typical strategies that the algorithm learned. So first, the algorithm uses the same initial action to get the initial observation of the trajectory. And in the first example, it's actually the class land too close compared to the goal location. And in the other example, actually, the class kind of gets folded up because of high density. So in these 2 different cases, the algorithm is able to adjust its action differently, right? So for the first example, it's able to increase its speed in order to reach to further location. And in the second case, it will be able to reduce the speed in order to prevent the class to fold. And then the algorithm will continue to adjust this action until it's achieved the goal or converges. And it typically takes 3 steps for this task. So as you can see, this formulation of iterative residual policy is pretty general and can be applied for many tasks as long as they are repeatable, right? You can always reset the state and retry it again. And even with a very complex dynamic, this framework kind of works for them as well. like for example, deformable objects. So if we want to kind of summarize kind of what we learned from this project, is that instead of learning the full dynamics model that's directly mapped from the action to effects, I think the algorithm can learn and make use of the residual dynamics. Just like in the rope example, learning the full trajectories from the action is hard, and decoding the precise physical parameters is hard, but learning how to change our action would affect the trajectory is much easier. At least the general direction is much easier. And also those kind of knowledge can generalize from one rope to the other rope, right? Even from one robot setup to the other robot setup. So that is, I think, the key idea that allows this system to generalize so well for different dynamics and also different systems.
One quick question. How do you initialize here the first sequence of actions that you're going to use? Because I think that's probably the most difficult thing to do here.
Yeah, so actually the first action for the two different tasks, we use two different, slightly different way to initialize it. So for the rope task, given a goal, we actually use the average action so we have the simulation data, right? We generate with many different ropes that we train on the simulation data. And then we can compute the average best action regardless of the rope. So we can kind of compute all the average trajectories and compute what is the average action that you can use regardless of the rope. And then that is the initial action. And for the class task, we actually just randomly initialize it with the same initial actions regardless of the goal.
I see, thanks.
Yeah, I think it's actually interesting to test whether it is very sensitive to the initial action. I have a feeling that it's probably not that sensitive to the initial action. My feeling is that it probably only take a few more steps. Why I feel that is when we change the, for example, the embodiment of the robot, the average best action is actually very far from the actual optimal action. And I think, yeah, the initialization we provided to them, I don't think it's that meaningful anyways.
Okay.
Do you mind like explain a little bit more about this residual dynamics that you're learning?
Yeah, so this is actually a very simple model. Let me go to the slides. So maybe we can look at this slide. So basically, the input to the network is the current observation. So if you look at this image, you have the trajectory of these actions, the trajectory as a result of the current action. And then this trajectory represented as an image is the input to the network. And additionally, they take another input, which is the delta action, which is how you're going to change the action. Right? For example, increase the speed. Right? And then you will sample a lot of different delta actions. So, and then for each of the delta action, you'll predict what will be the resulting trajectory if you apply that delta action. So basically what the system needs to learn is that if I increase the speed, I need to kind of increase the radius a little bit, for example. And then from the predicted trajectories, then you pick the one that's getting closer to the goal. Yeah. So there are also something that like we need to do in order to sample the better action. So basically you can sample it based on the current error. And when the error is large, you want to sample it further away, and then you can reduce the radius and getting closer to the optimal action.
Okay, very cool. Thank you.
Cool. Any other questions? Yeah, hopefully, yeah, I think hopefully this, I kind of feel this idea is pretty general, and I think it's not just actually applicable for deformable objects. If, for example, if you're learning tossing, right, by observing like the landing location, and kind of we have this intuition of if I toss with higher speed, it will land further away. I think this is indeed an idea that can generalize across a lot of different tasks. Okay, so yeah, so that's all the three projects that I talked about. But before I end my talk, I also kind of want to mention a few future direction that I kind of feel is currently missing in like this area of research. So I think one obvious one is actually to think about how to better leverage state representations using state-of-the-art computer vision algorithms. I think in most of the project I talked about today, we're using a very simple perception module that either just tracks the class coverage or visible key points, right? However, for more complex class manipulation tasks, like helping someone get dressed, will definitely need benefit from more detailed state representation. However, I think estimating the full state of a deformable object is still a very challenging task, even in computer vision, due to its high degree of freedoms and self-occlusions. I think so far I haven't see a very good algorithm that's able to fully address this problem. And another direction I think is also kind of related to the question that people ask me is how to automatically acquire or allow the robot to learn or acquire this kind of dynamic manipulation strategies, right? So and especially how they can learn it by themselves, right? So far what we have done is kind of identify those useful primitives like Fling, like using errors, like swing, right? And then we manually engineer those primitives and then learn the parameters for them. However, there is actually a very large family of dynamic manipulation strategies that's out there. And it is impossible for us to engineer every single one of them, right? So can we allow the robots to automatically discover those kind of useful strategies and use them for a given task? I think it is possible, and also feel it is a very critical and necessary next steps for achieving efficient manipulation for deformable objects. Yeah, so I think hopefully by now that you're convinced that dynamic behaviors are very critical for achieving efficient and robust object manipulation, especially for deformable objects and other undergraduate systems. And hopefully in the future, when you're designing robot manipulation system, you can also kind of consider to incorporate some of those elements of dynamic manipulation. And that's the end of my talk. I'm happy to take more questions.
Thank you, Shuran. It was a great talk and it was very interesting. So I open the floor to anyone who has any questions for her, and yeah, go ahead.
Hi, Shuran. I have a question. So I was wondering if you have any general thoughts on the ability to do sim-to-real transfer, especially in the context of deformable objects.
Yeah, so I think the last project, the residual dynamics project, I think that provides one way of thinking about how to do sim-to-real, right? So in simulation, it's very hard to model everything in simulation, and also because of the parameter that you measured may not be off, maybe because you didn't measure or consider all the physical parameters. But if you can learn something useful in simulation, and in that case, is this kind of changing directions of the dynamics or the residual dynamics. If you can learn that, and that part can be used to do this sim-to-real, then you can actually rely on the real world observation when you are actually executing the action in order to do the sim-to-real adaptation. But I have to mention that for those kind of methods, I think one of the biggest limitations is that the system need to be repeatable because not a lot of tasks that you can just try multiple times to get the goal, because once you try it, the state is changed and you cannot just adjust your action again and try again. So that's another additional challenge.
Thank you, Shuran. And also, what other kind of deformable objects other than strings and clothes do you think are interesting to work on as future directions? I'm curious.
Yeah, there are so many deformable objects, right? I think the class, for example, a big category is garments, and I think a big we are dealing with it all the time, and actually helping people get dressed. I think that is actually one very practical applications as well. Yeah.
Thank you, Shuran. Great talk. Thanks.
I have a question about the I guess the last project that you talked about. So in the examples that you show, like when you change the embodiments or the actual system, or I guess the string properties, that is the same frozen residual dynamics network, but just that was trained on one particular embodiment, but you're showing it's transferring. Is that right?
That's correct. Yeah. So that is the same model that we trained with simulation, that with one embodiment, basically the last link length is fixed, and then it's directly tested on other embodiments. It
Okay.
take them a few more steps to get to the goal, but it's able to adjust.
Right, right. Yeah, it's a really nice idea. I like it a lot. Also, I wanted to ask if you can possibly expand on the very last statement you said on in terms of future directions on. You said you're quite optimistic about the possibility of learning the right primitives from self-supervision. I'm just sure. I'm just wondering if you can elaborate on that, like why you're optimistic or where your intuition is on the right way forward.
Okay, so why I think it's very possible, I think that's like personal hope, because I feel it's very important, right? So as I said, there's no way that for us to kind of manually engineer all the possible useful primitives. And I think self-supervision is probably one way to do that. And actually another direction I recently think more about is how to learn from humans. I think, as I said earlier in my talk, most of the inspirations that we get of designing our primitives is looking at how humans do the task. So I think that indeed give us a very good initial starting point of thinking about what kind of dynamic action we should incorporate in our robots. I think our robot hardware is in a state that actually can do a lot of things, very capable. Yeah, I think we haven't fully leveraged them by just giving them the limited action space of quasi-static actions. Yeah.
Great, thank you so much.
Any other questions? Okay, I think we can conclude then. Thank you again for coming, and we hope to see you again. It was a great talk.